All right. Let's talk about combination probabilities. So we have been talking for a while now, several videos I think, about the different combinations. We've done a few combinations already, such as the AND probability, which looks like the probability that A will happen and B, both, okay? Now what we haven't done with this is we haven't quite talked about some of the mathiness of it, so let me get into that. The notation we would use for this would be probability of A, and it'll be an upside down U, B, A, upside down U, B, and in mathematics we see this little symbol here. This U upside down means intersection. Okay. So, and we generally say that an intersection is where both of those things occur. So, for instance, if you were driving on a street, if you were in Commerce, maybe this is Live Oak Street and this is Monroe. Okay. If you were driving on Live Oak Street and you came right here in this spot where the two streets overlap, and then you wanted to take a right on Monroe, which street are you on when you're right here in the middle? Okay, think about that for a second. Well, in my head I hear you saying, well, you're in the intersection of Live Oak and Monroe. Okay, you are on both at this moment right here, this little bitty square that is considered the intersection of Live Oak and Monroe. You're on both streets at the same time, right? Okay, so that's the way I think about those. So hopefully that'll help somebody to keep that intersection thing straight. Okay, so what does that mean? Okay, say I'm rolling dice, okay, fair two-sided dice, fair six-sided dice, and I want to know what's the probability that I will get a 3 and a 4, okay? Now, if it's a fair six-sided die, then those are independent events, right? Nothing, whatever I roll off the first one will not change the probability of the second one, so they're independent. Now, in our case, we would say we could even roll, say, a red die and a blue die at the same time. So what's the probability of a 3 and a 4? Well, mathematically, that looks like 3 intersect 4 with the little upside down U. And we know that whenever we're doing this, we said we're going to multiply, right? So whenever we're working on these kinds of intersections, the ands, we've said 2 or 3 times, we've done several problems like this where we would multiply, right? So the probability of getting a 3 on that six-sided die is a 1/6 times the probability of getting a 4 on that six-sided die is a 1/6. So we just multiply, we get a 1/36. So it's a 1 in 36 chance that you'll roll either 2 different dice or 1 die 2 times, either way, it doesn't matter, and get a 3 and a 4. 1/36, no problem. Okay, well, that kind of coincides a little bit with what happens whenever we're talking about an OR statement. Okay, so there's the OR probabilities. We've talked about these. And what I usually tell my students is that in the English language, it's the very inclusive OR, okay? So you have to be a little bit careful. There's an exclusive OR, meaning like, well, you can either fix your attitude, young lady, or you can go to your bedroom, okay? You can do one or the other. It's not inclusive at all. You only have one option. You have two options, but you can only do one of the things. That's an exclusive or. This is an inclusive or. So this means we don't care which one you're in, okay? If you're, for instance, if I was going to take all of my classes to go get ice cream as some kind of a treat or something, I would say, well, I don't care if you're in my stats class or you're in my math history class, okay? If you're in my stats class, you get to go get ice cream, or if you're in my math history class, you get to go get ice cream. So those are very inclusive ors. I want you, whether you're in this situation or that situation. So that's what we mean by inclusive. We're including anything in one group or anything in the other group. We don't care. Okay? So in this case, whenever I'm talking about that, we have said before, well, this is addition, right? That's where we were the other day. Now, we haven't thrown the notation at it yet, and that's what we're going to do right now. So this would be the probability of A or B. Okay. Probability of getting A or B. Okay. And the notation for that, the mathiness of it, is the P, A, and it looks like a small U, B. Okay. And that U right there is union. U means union. Okay. All right. So when I think about union in this particular case, I think, well, what about, say, a union in a marriage? Or, oh, here's a great one. What about a union that is the United States? Okay, the United States. Well, if you're in the union, that is the United States, do we care if you're, well, we might care if you're in Texas, because Texas rocks, woohoo. But if we call the Union of the United States, and I am not an artist, so please forgive me. Here's the question. Say you're like in, I don't even know which one's which direction. I can't remember. New Hampshire and Vermont. These are my New Hampshires and Vermonts. And then right beside them is Maine, right? Going up like this. And again, not an artist, so sorry guys. Down here is somewhere is Connecticut and different ones. But here's the question. If you're in whichever one this is, I'm sorry, New Hampshire or Vermont, does it matter? Are you still in the United States? Yeah. So if you're in this one, you're in the United States. If you're in this one, you're in the United States. If you're in Maine, are you still in the United States? Are you still in the Union? Yes. So you can be in Maine or New Hampshire or Vermont or this one's actually Massachusetts, I believe. Okay, and then I think Connecticut's down below that with, yes, I don't know. I don't remember. Massachusetts, maybe Massachusetts below that. Anyway, I thought Massachusetts was above. Anyway, it doesn't matter. Sorry, I'm sidetracked. Does it matter if you're in Connecticut? Are you still in the Union? Yes. So it doesn't matter. Any of these states, and here's a terrible drawing of the U.S. Okay, but you get the point. It doesn't matter if we're down here in Florida, and it's certainly not to scale, right? Doesn't matter if we're in Florida, if we're in Texas. Any of the states count. They all are part of the United States. So it's an or statement, okay? So let's go back to our probability of 3, but let's make it an or. Probability of 3 or 4, okay? Well, the mathy notation is probability of 3 union 4. Okay, oops, I am so sorry. I did intersection. Union, it's the U. U is for union, that's what I always tell my students. U is for union. Okay, 3 or 4. Well, what was the probability of 3? 1 out of 6, right? Okay, but instead of multiplying here, because we want you if you have a 3, or we want you if you have a 4, instead of multiplying, we're going to add. What's the probability of these people getting a 4? 1/6, right? Okay, well, what's 1/6 plus 1/6? That's 2/6. And of course, I can reduce that if I want to 1/3. Okay, so that is a different probability than what we had up here when it was 1/36. Is everybody all right with that? Okay, so I actually wanted to do this in the last video and I just didn't quite get there and I was running out of time, so I skipped it. But here's my question that happens a lot, and it happens a lot whenever you're in, like, say, Vegas or something like that, doing some gambling, and you want to know the sum of two dice. Two fair six-sided dice. Okay, this would happen at the craps game, right? Okay, where you might want to hit a 7, or you might want to hit an 11, or you might not want to hit snake eyes, which is a 1 and a 1, right? That kind of thing. So you might have to be careful of those things. So the question becomes something like, well, what's the probability that you roll two dice and the sum is, let's just say 7. Probability you roll two dice and the sum is 7. Okay, well, this is where you might start seeing some of the tables coming into play. So a lot, and I've got one that I've stolen from a book, so I'm just going to throw it up here so we can see it. A lot of times you'll start seeing tables for some of these problems because it makes life easier. So here is a table that's outcomes and sums for the roll of two dice. Across the top you can see the roll of the first dice, a 1, a 2, a 3, a 4, a 5, or a 6. And down the side here you can see the roll of the other die, 1, 2, 3, 4, 5, 6. Okay, and then each of these rectangles in here has the sum. This one plus this one is 1 plus 1 equals 2. The sum of this guy plus this guy, 1 plus 2 equals 3. 3 plus 1 equals 4, and so on. So if I rolled a 4 on one die and a 4 on the other die, a 4 plus 4 equals 8, right? So in this particular chart, they figured out all the combinations, there's that word, combination, where I can roll two dice and I get an 8. Okay, they were looking for 8s. So 6 plus 2 equals 8, 5 plus 3 equals 8, 4 plus 4 equals 8. They've got 3 plus 5 equals 8. Now look at that one and look at this one and be careful about it. Why do they have it listed twice? It's one's 3 and one's 5, so why is it listed twice? Think about the situation where you have a red die and a blue die. If you have two separate dice, and that's what this is saying, the sums for the roll of two dice, if one's red and one's blue, then if this one, the 5 is blue, that is different than this one, the 5 is red, right? Okay, so it's a 5 here, but a 3 here. And it's a 5 here, but a 3 here. So be careful about that. And they also have the 2 plus 6 separate from the 6 plus 2. And again, that would be red die versus blue die, or however you want to think about that. There are two different dice. So we need to list them all. So for our question, I asked about the sum being 7 because 7 is important in the craps game, right? There's a 6 plus 1, a 5 plus 2, a 4 plus 3, a 3 plus 4, a 2 plus 5, and a 1 plus 6. Well, that's 1, 2, 3, 4, 5, 6. What's the probability of each of those? Now let's think about it. This is the probability that one of them is a 6 and the other one is a 1. That's an and. That's a multiply, right? So that's a 1/6 times 1/6. That's the 1/36 we just did a second ago, right? This is the probability that one is a 5 and the other is a 2. Well, 1/6 times 1/6 is 1/36. But I have 1, 2, 3, 4, 5, 6 different cases of that. Okay? And here's the kicker. I want this one. That one counts for my sums adds up to 7. Or this one also adds up to 7. So I want him, right? Or this one also adds up to 7, or this one adds to 7, or this one adds to 7, or this one adds to 7. And remember, it's inclusive. I want them all. We're not going to talk about the United States, but kick Texas out of the union, right? If you're in Texas, then you're part of the union, and you get to count. You get to go get ice cream or whatever it is we're doing, right? Okay, so there are 6 different cases. So let's think about that for a second. Okay, the individual case, the probability of 6 plus 1 was 1/6 times 1/6. That was a multiply, gave me 1 over 36. So each of these individual cases where I get a 7, 6, I should have said and a 1. I should have used 5. Oh my goodness, I'm messed up on my notation today. I should have used the intersection, right? The probability that I'll get a 5 and I'll get a 2, again, 1/6 times 1/6, that's 1 over 36. So if each of these is 1 over 36, probability of 4 intersect 3, 136. Probability of 3 intersect 4, we did that one a little bit ago, 136. Probability of 2 intersect 5, 136. And last but not least, probability of 1 intersects 6, 1 over 36. And this one was 6 intersect 1, 1 over 36. Okay, each of these is the individual ones, but I want this one or this one or this one. Any of those count. If I'm rolling craps and I roll a red die 3 and blue die 4, it does not matter. It still adds up to 7 and it will count, okay? It gets to go to the party, so to speak, okay? So any of those work. So in the small individual probability, I did multiplication. But to do this overall probability, what I'm after, roll 2 dice, the sum is 7, that's an OR. Right? So that's like this. I want the probability of 6 intersect 1 or 5 intersect 2. I want this one or this one or this one. 4 intersect 3 or 3 intersect 4 or 2 intersect 5 or 1 intersect 6. I want the probability of all of those. Well, I've got it, right? This is a 1/36. This guy's 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 a 1/36. So I've got all of those, right? Okay. I just need to, actually I need to get rid of that P because I'm going to go ahead and add them. Okay, so it's no longer our probability. It's just I need to add them, right? Well, what happens there? Remember we talked about this. They all have the same denominator, so I'm going to keep the denominators the same. I'm just going to add the top. So this is 6/36. Or if you wanted to reduce it, it's a 1 in 6 chance. So that's why people play craps at the gambling tables, is because they're like, oh, I've got 1 in 6 chance. It's not impossible to get that 7 or whatever. So, and there are different rules with craps. It's just that that's the one that comes up a lot. So that happens, right? So what are your odds of rolling and getting a 7? Well, it's a 1 in 6 chance that whenever you roll 2 different dice, you'll get a sum that is 7. Okay, so that's what's going on with that. Okay, and I meant to do that one the other day. I just smooth ran out of time. All right, let's keep going. We got some other combinations we want to talk about. So all of the ones that we've been doing so far, we've been talking about non-overlapping events. Non-overlapping events. Okay. What the heck is she talking about? Okay. It means they didn't have anything in common that they could have shared. So the red die and the blue die, the roll for the red die basically has nothing to do with the roll for the blue die, right? If I had a group of students in my stats class, which is traditionally speaking freshmen, and I take them to my ice cream party, and I have a group of students in my math history class, which is traditionally juniors and seniors, and I take them to my ice cream party, are they going to have any students that overlap? Well, probably not, right? They're probably separate groups, separate populations that I can pull from, for lack of a better word. So let's do it this way. This is probability of the event A happening, and this is the probability of the event B happening. Okay, so think A is the probability that I spin my spinner and I get an A, okay, and B is the probability that I spin a spinner and I get a B. Is there any overlap between those two? Well, no, especially if we make the rule that if it lands on the line between them, we spin it again, right? We're not going to count that. It needs to be firmly in one set or the other. So those are not overlapping. They don't share any characteristics, so to speak, okay? That's what we've been dealing with so far, all the things we've been dealing with so far, okay? However, sometimes we will have overlapping. These, by the way, are called mutually exclusive events. Mutually exclusive. That just means you don't have anything in common. You're exclusive of each other, okay? My two classes don't have any students in common, okay? Now, if I was teaching a class where I taught maybe a developmental math class and I taught the stats class, then maybe there could be some students in both of my classes because we have something called co-requisite math, right? Where some students could be in both of those classes. Then I might have some overlap, but here I don't. These are separate. Okay, we'll say separate populations. Okay, separate groups, separate outcomes. Maybe instead of populations, let's say separate outcomes. I like that better. I don't want to use that population word too much. Okay, so what then? What the heck are we talking about? What if we're talking about inside of my class and I actually have some data where I pulled a group of students from one of my classes that I met face-to-face, and I said, okay, what's going on over here? How many people do I have in this class who wear glasses? And I literally went around and counted, okay? There were 3 people who wore glasses. And then I said, how many of you are wearing hats? And we went around and we counted, and there were 6 people who were wearing hats. But the difference is there were 7 people wearing hats. But the thing is, I couldn't just go in and put 7 here because there was one person who was wearing both glasses and a hat. Oh, they overlap. Notice that my 2 circles are overlapping here. These are people with glasses in the class. These are people with hats, and I had one person in the overlap, which means this person is wearing glasses and a hat. Uh-oh, what does that mean? That means they're in the intersection. Okay, they're in the intersection. Okay, well, then if there was one person who was wearing both, if I knew there were 3 people wearing glasses, how many people were over here? And I'm hearing in my head, hopefully, there were 3 in here, minus this 1, 2, right? 2 people were wearing glasses, but not a hat, okay? And if there were 7 wearing hats, but one of them was wearing both, hats and glasses, then how would I figure out how many were wearing hats but not glasses? Okay, and we're having to do a little arithmetic here, which is not terrible math, but we just need to keep up with it. 7 minus 1 gives me a 6 over here, right? Okay. So what happens here is that I don't want to double count this guy who's wearing both glasses and a hat, and I think it was a guy. Okay, so be careful that we don't double count him. That's what we've got to watch out for. So that requires me to do a tiny bit of arithmetic. I subtracted him out, right? Now he still counts once. He's right there in the intersection, okay? But I don't want to double count him. So if I just added the 3 glasses and the 7 hats, I would have 10 people in those 2 circles, right? But when I look at it, because I adjusted my numbers for this guy in the overlap, I've got 1, 2, 3, plus 6 is 9. There are actually only 9 people in here. It's just that that one guy has both. He's in both circles, right? If I cover up this circle, he's in the glasses circle. Yeah, he should be, right? Because he's wearing glasses. If I cover up this circle over here, he's in the hat circle. Yeah, he should be because he's wearing a hat. So 6 plus 1 is 7. 2 plus 1 is 3. So if you're not sure, do the really advanced math tactic of covering one up. It's the cover up method, okay? So I've got 9 people there, not the 10 that we might have thought of. And then here's a thing. There's my N for the class is total of 21. Okay, total of 21 students. I'll put that on the outside. What does that mean in here? Right here, I want a number. And this number is usually called the universal number, just FYI. It's the number of people who are in the class. The class is represented by the rectangle here, right? I guess I could put that over here so everybody can see it. Okay, the number of people in the class, but who aren't wearing glasses and they're not wearing a hat, right? That's how many people are out here in this open space. Well, let's think about that. How can I figure it out? Well, total is 21, and I've got 9 in the circles. What's that? 12, right? Okay, so there should be 12 people in the class, if I counted them up, 12 people who are in there, but they're not wearing glasses and they're not wearing hats. Okay, so we have to be a little bit careful. We have to do a little bit of mathiness with these things and watch it a bit. Okay, but it's not impossible, so we just keep an eye on it, okay? Let's see. Hang on just a second while I work through a couple of problems. All right. I'll come back to that one. I have a problem here, but I want to actually probably keep it in the next section, so we'll be back. Okay. The other day we were doing some expected value and different ones like that, so I just want to make sure that we get one of those going. Yeah, I got that. Okay. Okay, I'll come back to that. Let's do this problem. Say you're working a question on a test, and there are 4 true-false questions. Okay, so let's say Susie Q is taking a quiz with 4 true-false questions. She doesn't know any of the answers, so she will guess. Okay, so the questions are, there's multiple questions here. Find the probability that she will get 1 correct. Let's start there. Okay, so let's think about this. There are 4 questions. We'll make 4 boxes here. 2, 3, 4. And if she's just guessing and it's a true-false question, what's her chance of getting the correct answer? There's 1 correct answer, right? The answer for question number 1 is either true or false. And she's got 2 options. 1 correct answer out of 2 possibilities, right? So she's got a 50-50 shot of getting it correct. Does everybody agree? She's just guessing. No answer at all. Okay, This one, problem number 2, still got a 50-50 shot, okay? 50% probability of guessing and getting it correct. And that's true of all 4 questions. Is that all right? All right. So what's the probability of her getting 1 correct? Well, that's a 1/2, right? 1 out of 2 chance, okay? What's the probability of her getting 2 correct? Now we're going to have to be careful about this one, okay? What does that mean? It means she gets a correct answer and she gets another correct answer. She wants both of those things to happen, right? Okay, so she wants both of those things to happen, then what am I going to do? It's an and situation. It's a probability of correct intersect correct. She wants both of those things to happen. And, well, that's a what? Multiplication. 1/2 times 1/2. Is everybody okay with that? We're going to multiply. All right, so that's a 1 in 4 shot. You've got a 1 in 4 chance, Susie, of getting 2 of them correct when all you do is guess. Well, that's only 25%. That's not very good, okay? 1 in 4 shot. All right, how about this one? Probability that you'll get 3 correct. Well, that's the probability of a correct and a correct and a correct, right? Number 1 has to be correct. Or one of these, it doesn't matter which one. One of these has to be correct, and another one has to be correct, and another one has to be correct. So those are 3 multiplied together. So that's 1/2 times 1/2 times 1/2. I hope everybody sees what I'm doing here. Okay. So 1/2 times 1/2 times 1/2, that's a what? 1/8. 1 in 8 chance that you guess on 4 multiple choice questions and you get 3 of them correct. It's not very much. That's only like 12.5%. It's very low. It's unlikely to happen. All right, and the last one, what's the probability that she gets all 4 correct? Well, that's a correct and a correct and a correct and a correct, right? So multiplying 4 times. This one's correct, this one's correct, this one's correct, this one's correct. So that's a what? 1 in 16 chance. All right, so that's not terrible. All right. What's this 1 in 16 chance, by the way? It's very low. It's only like 6%. Okay, so she's not doing very well. She's not very likely to get 4 correct. But what if we said this? What's the probability that she gets 1, 2, 3, or 4 correct? 1, 2, 3, or 4 correct. Well, that's actually all of these. She gets 1 correct, or, now what was the difference with the or? Or was add, right? Okay, so she gets 1 correct, or 2 correct, or 3 correct, or 4 correct. Well, what does that look like? It's a 1/2, and we're doing ors, so that was a plus, right? So plus 1/4, or 1/8, or 1/16. So it's a 1/2 plus 1/4 plus 1/8 plus 1/16, right? Probability of 1, 2, 3, or 4 correct. It's hard to write that one out, but that's what we're after. Okay, so it's a bunch of adding going on there. Okay, well, we got that. All right, so how the heck do I work that one? A bunch of different denominators. I need to get a common denominator between all of them, and hopefully we know that the common denominator here is 16, right? Okay, so 8/16 plus, this one would have been times 4, right? So 4/16. Get your common denominators, get an equivalent fraction. 1/8, this would be times 2 over 2, so this is 2/16, and this is 1/16. Okay, so 8 plus 4 is 12, plus 14 is 2, plus 1 is 15/16. All right, so that's not bad. That's really close to 100%, right? In fact, that is a 93.75% chance that she'll get 1, 2, 3, or 4 correct. Well, that shouldn't be so shocking because what are we saying? This is any of them are correct, basically, right? She gets one of them correct, or 2 of them correct, or 3 of them are correct, or 4 of them correct. The only situation that doesn't cover, let's think about that, is the probability that she misses all 4. Right? Probability that she misses all 4. Well, what would that look like? The probability that she misses all 4 would mean she got the first one wrong. Well, what's the probability of that happening? Well, there's one wrong answer out of 2, right? So 1/2. And that's a multiply. She got the second one wrong. So what's that probability? 1/2. And she got the third one wrong. So what's that one's probability? 1/2. And she got the fourth one wrong, so what's that one's probability? She missed them all. 1/2. 1 out of 2 is her chance of getting that one wrong. Well, we've already done this. 1/2 times 1/2 times 1/2 times 1/2, that's 1/16. Okay. Missed them all. Okay. This has got something, basically. She got something correct. She got a 15 out of 16 chance of getting something correct. She's only got a 1 in 16 chance of missing them all. So that's, like I said before, that's only like a 6% chance, and that makes sense because almost 94% chance that she'll get something correct, right? So what does that tell you, by the way? If you're on a true-false question and you're guessing, you should guess. Don't just leave it blank, right? Because you've got, the more true-falses there are, you've got a chance of getting something right if you guess versus missing them all. It's only a 1 in 16 chance, less than 6% chance. Okay? There's another way to figure this probability if you wanted to. I'm fine with you just saying, oh, we missed that one, missed that one, missed that one, missed that one. 1/16. What if we said the probability of missing all 4, what if I said that's the same as the whole entire thing, all of the outcomes we have, minus got something correct? Is that also true? All of my possible outcomes minus you got something correct, which would be 1 correct, 2 correct, 3 correct, or 4 correct. That's this guy right here, right? 15 out of 16. Well, wouldn't that be 1 minus 15 out of 16, which is 1/16? Isn't that the same thing? Yeah, those are the same. So there's more than one way to get around to that particular statistic. So don't feel like, oh, it's got to be done this way. That's not necessarily true. You just have to be able to kind of support your reasoning and go for it and make sure it makes sense. Okay, so here's some interesting stuff. There are 2 different words that I've kind of been avoiding a little bit just because they're mathy words and I don't really care about them. There's 2 different words. One is called combinations. Okay, and the technical mathematical term for these is whenever you talk about combinations, order doesn't matter. So that means I get rid of duplicates. So in the case that I'm getting a grab bag and I say, what's the probability that you draw 2 cubes out, and one's a red and one's a green? Okay. Well, in this case, the order doesn't matter. So this is actually the same outcome if I draw a red first and a green second, would be considered the same outcome as if I drew a green first and a red second. Because it's just, what's the probability that I get a red and a green? I don't care which order it is. Okay? So when that happens, we would count these equally, okay? And we say we get rid of the duplicates. That just means that we don't care that they're duplicated, okay? It's all good. However, there's a different kind that makes, order does make a difference, okay? That one's called a permutation. We're not really going to go too far into this in this class. I just want you to have seen them and know that they're out there. In permutations, order does matter. Okay, so this would be like, okay, I'm going to put everybody's name in a hat, and I'm going to draw out. And the first person I draw, first person's name I draw, you're going to be the president of our new club. Okay. The second person I draw, you're going to be the vice president. Okay, so I'm filling in slots, so to speak, and it does make a difference whether you're a president or a vice president, right? Okay, so there are different duties for that, so it does matter who's first and who's second. So the probability that I drew, in this case, probability of red-green does not equal the probability of green-red. Well, I'm not going to say the let me get rid of the P's here. Red-green is not necessarily the same as green-red, because here red is the president and green is the VP, but here green is the president and red is the VP. Okay, probabilities might actually be the same, so I'll dump that P out of there. I'm sorry, but that particular event is not the same. If this is Matt and this is Susie, then Matt being president is different than Susie being president, right? So we got to watch out for those. Okay, so those are called permutations, and if you see those, it actually, you have to be a little more careful with those because the order does matter. So I can't just say, oh, that's the same thing. Okay, they're not necessarily the same case at all. You have to watch out for those. All right. The next thing, what about some of these overlapping things? So I'm just going to work a couple of problems. We've got some examples already. I'm starting to run low on time, so I just want to make sure that we look at them. I said I drew those circles earlier, right? Well, those are considered, they're called Venn diagrams, just so you know. It's called a Venn diagram. Okay. You probably don't care what that circle is called, but that's what it's called. Okay, so I had the Venn diagrams earlier, but I said sometimes when you start working these problems, you'll start seeing tables. And the tables are going to tell me something about if there's some of these overlaps going on, if I need to care about them, or if I don't need to care about them. Sometimes if there's an overlap, I don't want to count those duplicates, so I'm going to get rid of them, right? Okay, so let's see what we've got here. There's a problem, and I took this out of a book somewhere. It's called Minorities and Poverty. Okay. And what it says is that Pine Creek has 2,350 people. Pine Creek has 2,350 people. Okay. Out of those, 1,950 are white and 400 are non-white. Okay, so we're talking about a basic demographic breakdown here, right? So they're just looking at ethnicities. Some problems would talk about ethnicity with gender, stuff like that. But we're just talking about and they're being very generic here, right? White versus non-white. So we don't know any of the other subgroups or anything like that. And everybody knows that white doesn't necessarily mean white, so there could be subgroups in there, but this is just a very general problem. That's the way that they're giving it to us, okay? So here's what they say. 11% of the white citizens, so if you multiply that out, 11% of the 1950, that's 215 people live below poverty, below poverty level. Okay, so they're just giving us some, again, demographics, economic information. It says 28% of the non-white citizens, which again, if you multiply that, 28% times 400, that would give me 112 people live below poverty level. Okay. Find the probability of either of being, I guess, either non-white or, now that's going to be important for us, so watch out for keywords like that, living below poverty level. Okay, so let's be a little bit careful about this. The probability of being non-white, okay, let me come back here, 400 are non-white. Probability of being non-white in this particular town is what? Let's do the relative probability here. 400 are the non-white, that's what I want on top. That's the situation I'm looking for. Out of, what's the total number of people in this town? 2,350, right? Okay, and I can do some math and all that, but I'd like to keep the 2350 for now because I feel like I'm going to need that because I'm going to have to do some adding and subtracting in a little bit, so I'm going to just keep the common denominator because the total number of people in the town is going to be 2350 no matter what, right? Okay, so the probability of being non-white is whatever this number turns out to be, 400 out of 2350 in this town, okay? So we have to be a little bit careful here though because, so they've got or living below poverty level, okay, but they gave me two different groups who are living below poverty level, okay. They said 11% of white citizens live below poverty level and 28% of non-white citizens live below poverty level. So we have two different numbers, okay. So let's see that. Probability of non-white below poverty. Well, we said the non-white below poverty was 112 out of the 2350, right? Probability of white below poverty level. They don't just want non-white people below poverty level, right? They said or basically anyone living below poverty level, right? Well, that is white citizens living below poverty level, 215 out of 2350. And last but not least, what's just the probability of being a white person in this town? 1950 out of 2350. So they're giving me a lot of information here, and I can do a lot of stuff with it, but I want to make sure I'm using the correct ones whenever I come in here and I try to find this probability they've asked for. Now, here's where a particular table might come in handy. Okay, so that's what we've talked about before. I just mentioned a little bit ago, is there sometimes there's a table. So the table in this case might look something like this. I'm going to make a rectangle over here. Okay, and let me come right here. I'm just going to have, let me do this. All right, down the side here, I'm going to put white and non-white. And across the top, we're going to be not in poverty. And we're going to say below poverty level. Okay. So let's be careful about this because the total number of white people in the town was 1950, right? Okay. But we have to be a tiny, tiny bit careful because they're not all at poverty. We found out that the people in poverty was 215, right? Yeah. So what does that leave me here? I feel like my number's messed up a little bit. Okay, my number is 1,735. Okay, so do some subtraction real quickly. Yeah, 1950 minus 215. We've got that 1,735. We're white and not in poverty. Okay. What about the non-whites? Well, the number we know is the 112 who were at poverty level, right? But there were 400 of this group. Okay, so when I subtract that out, I should have 288. So what this does whenever I start looking at these groups, we have to be careful because if I just talk about non-white people or I just talk about white people, the people who are in these subgroups, so to speak, white people below poverty, those 215 people are in the 1950, right? So I need to do a little bit of arithmetic. It's similar to the Venn diagrams. This is just a nice table, and some people really like these because it helps them group them and see in what order they're looking at. So this is just a nice pretty Venn diagram, but it helps me to see, oh, what's going on here. Okay. So when I start working on this particular probability, let me put it down here again. Let me grab a green. Probability of non-white, or, so that's going to be a union, which means I'm going to add, right? Or living below poverty. Okay, and then again, there's going to be a couple of ways for me to do this, so I'm going to just show you a couple. Okay, so once I have it broken out into this table, it's kind of nice because I can do, and here's the trickiness of it, I can do all of the non-white people, which was 400, right? 2350, 400 out of 2350, that's their probability. Plus, because we're unioning, so I'm going to have a plus. Okay. I can do this several ways. Normally speaking, what people would do is they would say, here's all my below poverty people, and they would add those up. Okay. Well, if you add those up, it's 327 people below poverty. Okay. And you're just trucking right along. However, if you're not paying attention, or hopefully you're paying attention, you'll see this little overlapping area here. Who are those people? Those are the people who are both non-white and below poverty level, right? So here's the thing about whenever they have overlapping situations. We don't double count the middle. Remember that? I said that earlier. Don't double count the overlap. Okay? And so in order to watch out, if I put these people in here with this 327, then I'm in trouble because I already counted those 112 people over here in the non-white group, right? So I'm double counting them. So if you get in that situation, what you do is you subtract the overlap. I've double counted them. They get a vote, but they don't get 2 votes. Okay? So now I need to subtract the overlap, minus 112 over 2350. All right. So if I did that, then I just have to be careful. This is 615, just to finish that problem out. Okay. If I double count them, then I need to subtract them. Now, some people say, oh, I wouldn't do that. That's a lot more work. And if you're in that boat and you saw it and you're great, then that's fine. Some people would say, hey, look, the probability of non-white or union living below poverty, you can do it a couple of ways. You can either say, I'm going to count all the non-whites, and you just know, hey, those people are already in there. And then I'm going to add the 215 that are below poverty level. Okay, that would be the 615, so you'd be good. Okay, or they might say this, look, I'm going to add up the subgroups. 288 out of 2350 are non-whites not in poverty. They count because they're in this first group, non-white. Or 112 out of 2350. Those are non-whites in poverty level, so they actually count in both, so I want their count. Only once, though. They only get one vote. Or these 215 people up here who are white but below poverty level. Okay, they're in the second group, right? They get to go to the party also. Okay, so this would end up being the 400 plus the 215, which is 615. Okay, so we just talked about 3 different ways to calculate that really quickly. And that, I know it was really quickly, but I just feel like I'm running out of time. So when they overlap, you have to make sure not to double count. Whether it's that you add them in and then you go back and figure out, these are the ones I double counted, so I have to subtract them. That's okay. And in your book, there's actually a very clear formula for that. I'll give it to you in just a second. If that's the way you want to do it, then that is wonderful and it works out great, no problem. Or sometimes people are like, I don't want to come back and have to subtract. If you don't want to have to come back and subtract, that's okay. Don't come back and have to subtract. But that means that you're going to have to break them down into subgroups so that you can tell where's the not overlapping part and where is the overlapping part. So here it is real quickly. If you have overlapping events, okay, where both things can happen at once. Okay, this is my classroom where people can be wearing both glasses and hats at the same time. It is possible, okay? Then you have to watch out for double counting. So if you just do the probability of A or B, we're doing a union here, and you just do the probability of A plus the probability of B, then you're going to be in trouble because there are people who are in the intersection, right? And those people, if I just add them up in the first group and I add them up in the second group, that's the case where they're in the non-white group and the poverty level group at the same time, then I'm in trouble. They're getting double counted. So what I'm going to do is I'm going to subtract the probability of A and B. This is the intersection, right? Subtract that group out that could be in both. So that looks like probability of A plus the probability of B minus the probability of A intersection, that's the upside down U, B. Okay, so that's what that formula looks like. Only when you've got overlapping events, right? If these guys are mutually exclusive events, are they going to have an intersection? That's the 2 separate groups, my math history group and my stats group. They don't have anybody overlapping, right? So if I subtracted out the intersection, there isn't one. It's minus 0, right? So we don't worry about him. But you have to know that going in and not to be stressing out by him. Okay? All right, so I think that's about it for us. Just really, really watch out for those overlapping events. And, all right, yay. It's less than an hour, fine, barely. Have a great one. Let me know if you have questions. Thanks.